Hello there. We're gonna be starting in 2 minutes. I want to go over the biweekly contest, 111. As usual, it consists of 4 problems. The first one is about counting pairs. That satisfy some condition according to the name of the problem. So let's get started. I'm gonna share the link to the contest and the link to Q1. And let's start. Count pairs whose sum is less than target. So we are given an integer array nums of length n and an integer target. Return the number of pairs ij, I is less than j within the bounds of the array, and their sum is the sum of the corresponding values is less than target. And we get 2 examples here, so we can get negative numbers. So let's look at the constraints. The size is up to 50 and the values can be negative from -50 up to 50 inclusive. And there are 3 pairs of indices to satisfy the condition. So yes, let's check it out. So it's 0, 1, which is this 2, 0, 2, with 3 cannot be paired, and 0, 4, it's another one. Note that 0 is not counted, it's not strictly less, okay. And then we have a bigger case with 10 pairs. So yeah, this is an easy. So as usual, we should go for the brute force approach. At least we should consider the brute force search initially, and given that the size is n and we know that there are n square pairs, then it should be fast enough. So let's just code it. I'm first going to code it the same way you would code this in C++ or other programming languages. So we just go enumerate all the pairs. So I from 0 to length of nums exclusive, and then this goes from I plus 1 up to the end, and we check that the condition is satisfied, and in that case we count it and we return the total. So this should work. I'm pretty confident. We solve the examples and accepted. Cool. So now let's make it more Pythonic by, instead of doing the having a variable and incrementing it, we can use the sum function, and we can even put the condition as the value to some, because when the condition is true, this will be interpreted as 1, and if it is false, it will be interpreted as 0. So it will work. And this is a one-liner, which is always nice. I mean, we're not obfuscating the code, and it works as well. Cool. And now, as usual, let's try to go for a faster solution, a linear solution. This is obviously quadratic. If you want to count exactly how many iterations this does, you need to well, yesterday I explained the formula for adding the natural numbers from 1 up to some n, and here it's the same thing, because if you think about it, in the first iteration, when I is 0, then j is going to go from 1 up to n minus 1. So there are n minus 1 iterations. Then in the second one, you're going to have n minus 2, and so on up to the last one, which is going to be only one iteration. So that means that the total number of iterations is going to be 1 plus 2, so on up to n minus 1. And we know that for the formula, that if you want to learn how to derive it, you can see my previous video. It's going to be n times n minus 1 divided by 2. So how do we make this faster? So this is so usually the technique to make this kind of problem of counting pairs or doing something with pairs faster is and making it linear is to go over one of the elements of the pair and then trying to count or to find the other values quickly. This is similar to the two-sum problem, where you want to find two numbers that add up to a target. Once you fixed one of them, then you can solve the equation and you know what the other value must be, and you can quickly count it. So this is very similar. However, it's not by equality, it's an inequality. So it is useful to find the number where the equality holds, and then we want some way to count all the numbers that are less than or equal to that limit. So in other words, if we are considering position A, and we want to count all the numbers that are to the left of I, such that they satisfy the condition. So nums of, let's say this is j plus nums of I is less than or equal to the target. Hello, smart coder, how's it going? So like I said, this is equivalent to to this, we just manipulate the inequality. We're subtracting n of I, and so here we have a number, and we want to quickly know all the numbers in this range that we can add to a data structure. We want a data structure such that, let's call it S, and we want to ask how many there are. We want to count less than n of j. No, sorry. Target minus end of I. So we want to keep track of this data structure. What data structure has this kind of operation? Well, in Python, it's the sorted list, which is not part of the standard library, but it's available in LeetCode. It's the sorted containers module, and the method that does this that we want, it's called bisect, and it's bisect left, because if there are repeated elements, we want the leftmost, so that we count the numbers that are less than or equal to this value. So with that, we have enough information to write the code. So like I said, from sorted containers, we import sorted list, and we're gonna keep track of all the elements, and we're gonna keep track of the total. Here we cannot do one fancy one-liner because we are changing the sorted list, so it's kind of weird to do those kind of high-level functions with side effects. So let's do it this way. So we have the E element, or let's call it X, from nums, and at the end we're gonna include X in the set. We're gonna return res, and here we want to know how many, and like we said, we want bisect left of target minus X, and this is what we're gonna add to the result, and we get it right for the examples and accept it. So yeah, pretty standard kind of problem. It has, like I said, it has the two-sum type structure. So be aware of this trick. This is very general because we just we have an equation with two variables and one constant, and we're basically fixing, we're going over all the possible values of one of the variables, and then we're left with an equation that can be solved. It has only one variable. In this case, it's an inequality, not an equation, but it's the same thing. And take into account that this could even work for more than two variables. You could have sometimes, for example, you have the three-sum problem, and in that case you can go over all the values of two of the variables and then solve it for the remaining variable, and so on. So I'm mentioning this so that you can understand the pattern and solve more problems, not only the specific to-sum or counting the pairs that whose sum is less than some target, so on. So that's all for this problem. Let's go to the next one. Make string, let me share the link. Make string a subsequence using cyclic increments. So you get two strings with these names, and in an operation you select a set of indices in string 1, and for each index I in the set increment string 1 of I to the next character cyclically. Yes, sometimes they call it increment with wraparound, but yeah, here it is explained, and this is the key part, that C becomes A. Return true if it's possible to make string 2 a subsequence of string 1 by performing the operation at most once, and false otherwise. And here we get the definition of a subsequence, which is standard, so I'm gonna skip it. And here you can, because C can be converted to D, and so you have A, and D. Here you also can, because you can convert both C to A and C to D, and then you have the exact same string. And here you cannot, because there's no D here. Even if you increase A or increase B, there's not going to be a D. And the sizes of the strings are pretty big, up to 10 to the 5, so you have to do something linear and not quadratic. And so there is a simple way to figure out a simple algorithm, which is well known for checking if a string is a substring of another one. And that would be the case where you don't change string 1. So let me show you how that code would be. You just go over the long string and you keep track of the position in the short string, the shorter, and if they match, then you consume that character in the bigger string, and if at some point you reach the end, then you found a match, and otherwise you didn't. So this is going to work for the cases where the string is already, so for example, if it's already a substring, so for example, if we have AC, this should give us true, but if this was AD, like in the example, we're gonna say false, but the answer should be true. So The problem is that this can match to either string 1 of I or the next character, which is, let's call it next, and next of a character is going to be so in Python you turn a character into a number like this, and if you subtract from A, that is going to give you the index in the alphabet, and then we add 1 and we mod by 26 so that we wrap around, and then I guess we have to do this to get the corresponding value, and this. This might be different. You don't have these functions in C++ and other languages. So I think this should work. What did I do? Did I close? Oh, I'm missing one parenthesis here. Cool. And let's see the other cases. Too soon. True, true, false. So it's good. Accepted. So yeah, let me explain a little bit more. So this turned out to be a variation of the standard algorithm for checking, for deciding the subsequent condition. So let me explain why that works, and then it will be clear why we were able to make that modification. So again, we are considering the ith position in string 1. So this is string 1 and this is string 2, and we're considering here the shayth position. And so so there are two possibilities. If they don't match, okay, we move on to the next of x1, we increment I, and that's we don't have a choice. The question is, what happens if they do match? Is it always good to advance j and to consume it, or not? That's a valid question. Intuitively, it feels like you should consume it, but let me prove it. Let's say that we don't consume it, that we skip it, and so eventually we're going to have to match, instead of matching this to this, we're going to match this character to some other position. Okay, so to find a subsequence, we have to match all the values of, so here, for example, this is going to match somewhere along those lines and so on. But if we find a solution without making, this is the greedy choice, without making the greedy choice, we can always modify it. So we know that we cannot cross these arrows, right? Maybe we have an arrow here that goes that way, but we can always change this arrow and move it here, and we'll also have a solution. So this is why being greedy cannot make the situation worse. And that's why in this variation of the problem you also want to match as soon as possible. So if you find a match that is not exact, but it's by making a modification, by incrementing the character, the ith character of S1, then you should do it. So that's the justification of why this algorithm works. I think it's pretty intuitive, but sometimes it's good to formalize the intuition. All right, so let's move on. I'm gonna share my solutions at the end. Let me share this. Sorting 3 groups. The numbers from 0 are divided into 3 groups. Numbers from 1 to 3, where number I belongs to group nums of I. Notice that some groups may be empty. You're allowed to perform this operation any number of times. Pick a number X and change its group. More formally, change nums of X to any number from 1 to 3. A new array res is constructed using the following procedure. Sort the numbers in each group independently. Append the elements from groups 1, 2, and 3 to res in that order. And nums is called a beautiful array if the constructed array res is sorted in non-decreasing order. Return the minimum number of operations to make nums a beautiful array. So we get a nums array that has only values between 1 and 3 inclusive. Here's an example. Here we're changing this 2 into a 1, and this also into a 1, and this also into a 1, and we get all 1s, and we make 3 changes, so that's the minimum. And here, example 2, we can perform just 2 operations by, I think this is explained in a very convoluted way. We need to change them so that they are I don't know why they are talking about sorting the groups. You just need to change the numbers so that the ones come, so that is sorted. So in this case, it's already sorted, so you don't have to change anything. And here you just change this 2 to 1s, and you are done. And and the sizes are very small. The size of the maximum size is 100, and well, we already knew this. So one observation. I mean, this is a pretty straightforward problem. It's a medium. So we have to partition, basically, we have to partition the array into a first group has to have 1s, it could be empty. Then the second group has to have 2s, of course it could be empty, and the third group has to have 3s, and they have to come in order. So that means partition becomes determined by just having two indices. We can have a first index. Let me draw this. So we want to partition the array such that from the beginning we have we have this I variable and this j variable. Well, that's not a nice j. And let's say that the first group, the group 1, is going to be between 0 and I exclusive, and the group of 2s is going to be between I and j exclusive, and the group 3 is going to be between j and n exclusive. All of them could be empty, and once we have that, and there I and j are quadratic, and the size is 100, so there are not many possibilities. There are like 10,000 possibilities, and once we have this, we can count. We need to transform all the values here that are different than 1. We need to count them, because all of those we will have to transform into 1, and then all these all the numbers in this range, we have to count. What's that? We have to count the ones that are different than 2 here, and from here up to the end, we have to count the ones that are different than 3. And that's going to give us the cost of the partition. How do we do that quickly? Well, we could have a prefix. We could recompute prefix arrays, so that we know for every range we can know how many there are, how many 1s there are, how many 2s there are, and how many 3s there are. And that should be good. That should be good. We can have prefix arrays for, well, essentially 3 prefix arrays. So we have prefix array k with k between 1 and 3, or well, maybe it's easier to have it 0 based, but it's the same thing. And here, this is going to give us the sum of the array nums up to I in the slice notation of Python. So yeah, let's code it. Let's code it. So we're going to have three arrays. Let's make it so it has 3 columns and n plus 1 rows. Let's get maybe it's useful. So initially we'll have n plus 1 rows, because this is going to give us how many elements of that value there are in the first k elements. So let's see. So we go over the elements, we append a copy of the previous, and then we add 1 to this. That's right. No, we want the last element, and then we index by the zero-based value of nums, and we increase it. And now we are ready to go over all the possible values. I think we need to, since this is not, this excludes, we said that I excludes, it's excluded from the first range. I think we need to go to n inclusive, and then j has to be from I to n plus 1. So now we want to compute the cost, and let's count how many zeros there are in the range 0, I, how many ones there are, and how many threes there are, how many twos, it's zero-based, there are, and then we just want to minimize, so this should be initially infinity, and this is going to always have a possible value, so it doesn't matter. Yeah, I guess we could do this in a more Pythonic way. Right, and so now we need to implement that helper from ij and x. And how do we do this? The prefix, so j is not inclusive. Yes, so I think, so we want to count the ones that are different than x, right? Because those are the ones that we have to change. So let's call this y in range 3 if x is different than y. And so here we want the difference between this, and this should do it. Three to 0 is good. Accepted. Good. So it wasn't too bad. I think it was on the easy side. I don't know if you can get away with adding, because a million, can you get away with adding this on the fly? Do you actually need the prefix sums? I don't know. Well, in any case, this is pretty simple. Yeah, I think you should be able to do this. Maybe. But yeah, I don't think it's easier to code actually. Okay, so this is it. Let's go to the hard problem. You're given positive integers low, high, and k. A number is beautiful if it meets both of the following conditions. The count of even digits in the number is equal to the count of odd digits, and the number is divisible by k. Return the number of beautiful integers in the range low, high, inclusive. And they're up to 10 to the 9. So this means that you cannot go over the entire range. That will be too slow. And k is very small. This is at most 20. So that's something to pay attention to. So there is a technique to solve these kinds of problems, which is called DGDP, and it makes this kind of problem pretty simple actually. So let's say that we have a function that counts all these numbers from 1 up to, or from 0 up to a bound. Let's call this n. Why not? So then we could just count the difference between low and high, low minus 1, and that is going to give us the number that we want. Okay, so that already reduces the problem to only one bound. We can forget about the lower bound. But how do we count this? We need to implement this count function. So let's go to the drawing board. So the idea of DGDP is that we are going to do a DP over the digits of the numbers. We're going to be choosing the digits from the least significant up to the most significant digit. And so it's kind of a take it or leave it. I mean, we're making a choice between the 10 possible digits. We're choosing one, and then we're moving over to the left of the number. So that is simple enough, but we need to do it in a way where we keep enough information to make sure that when we finish generating all the numbers, we can decide whether they satisfy the condition or not. And for that, we have to keep track. Let's remember the conditions. We have to keep track of how many even digits we added. I mean, the numbers are going to have at most, I don't know, 10 digits. If it's 10 to the 9, at most they have 10 digits. So this is a very, if you think about the recursion, we're going to do this with memoization recursively. So the depth of the recursion is going to be very shallow. So what I'm saying is that the count of even digits, the total number of digits is going to be up to 10. So the number of subproblems, if we keep that as a parameter of the subproblem, it's going to be very small. So we need to keep track of how many even digits, how many odd digits we added so far. And then we have this condition that we want the number to be divisible by k. And one way to do this is to keep track of the remainder of the number by k, so that at the end we check if it is 0, which is another way of saying that it's divisible by k. The remainder is 0. So that's all that we need. There is a small catch, but let's start by, I like what I did in the previous streams, where we wrote the formula for the recurrence, so that, because it is language independent, and I think the idea is condensed. You can ignore some of the implementation details. So let's say that we have a function c that is going to receive this n, which is the bound. Then it's going to receive the count of odd digits, the count of even digits that we added so far, then the remainder mod k. So so we have some k variable here, and then for convenience we want to keep track of the, so we're going over the digits from right to left, and we want to keep track of the power of 10 that corresponds to the current digits. So let's call it p, and so there are a lot of parameters, but they're small numbers, okay? Because this can have, like we said, 10 values, or maybe 11 if you count. Well, let's say 10 to have a round number. This also has 10 possibilities, and the remainder has 20, around 20, because of the bound on k. We know that k says as 20, so it has 21, but we're rounding, and we can take the power. I mean, this is actually a redundant parameter, because if we know how many digits, if we add the odd digits and the even digits, we know how many digits there are, and that determines the power. So we don't need to count this for the subproblems. And then n, so yeah, here there's a catch, because n is big, it's up to 10 to the 9, but we're gonna be dividing it by 10, so we're gonna be reducing. So that means that this number is gonna be smallish, the number of, it's hard to pin down how many values it's going to have. At least I haven't thought about it. And then there is a catch, because since we are going to be generating the number from right to left, 0 is special, because when we put a 0, that could be a leading 0, and we don't need to count leading zeros as even digits. So we have to keep track of the number of leading zeros so that we can subtract them when we check whether the odd digits are equal to the even digits. So let's add LC parameter for the leading zeros. Okay, so now we have a few cases. If n is less than 0, it means that there are no numbers that between 0 and greater than or equal 0 that are less than or equal n. So there's 0, the count is 0 in that case. And if n is actually 0, then it means that there's only 1, it's 0, but we need to check that all the conditions are satisfied. And let's write this, there's annotation that we can write an expression here in square brackets, and if it's true, it returns a 1, and if it's 0, it returns a 0. If it's false, it returns a 0. So the condition is that the odd digits plus the even digits, but minus the leading zeros, we don't want to count. Those are even digits that we don't want to count. Well, it's not a plus sign, it's an equal sign. So this is equal to this, and the remainder, there are two conditions there. Odd digits equal to the even digits, and the remainder has to be 0, which means that it's divisible by k. And if these two conditions are true, there's one solution, and if they're false, there's no solution. And then there's a general case. Those are the two base cases. And then there's a general case where n is greater than 0, in which case we want to consider every possible digit. So we'll do a sum. This is how it is written in math notation, but it's the same in, so let's call it d, the digit, and it's going to be from 0 to 9 inclusive. Okay, and so we want to count, we want to do a recursive call, recurrence, and so we need to adjust n, and for that we're going to subtract the digit and do a integer division by 10, so that we move on to the next digit. Then we need to update the odd, so we want to add the parity of d to all the odd digits that we already counted, and then the same for the even, but it's the opposite, so we did subtract it from 1. And then we want the remainder. So the remainder is going to be r plus the digit times the power of 10 corresponding to the current digit, and all mod k. Then the power of 10, we want to multiply it by 10 for the next digit, and we want to mod it. And finally, the leading zeros, it depends on whether D is 0 or not. If it is 0, we use again this square bracket notation that gives us 1. So if it is 0, we want the leading zeros to be incremented, and if it is not 0, then the leading zeros is going to be 0. And so this is it. This is the whole solution, the whole recurrence. Now we translate it into code, which is very straightforward. So how many arguments do we have? We have 6 arguments. It's a lot, but it's okay, we know what they mean. Odd, even, then the remainder, and then the power of 10, and then the leading zeros. Okay, so base cases, if it's negative, there's 0. If it is 0, then we want, if the condition is satisfied, the odd is equal to the even minus the leading zeros, and R is 0, then it's 1, else it's 0. And finally, we want to make a sum for all the digits in the range, and we're gonna call count, and we want n minus d divided by 10, then the odds times d mod 2, even plus 1 minus d divided by mod 2, then r plus the digit times p mod k, then b times 10 mod k, and then again, if the leading zero is, if d is 0, then the leading 0 plus 1, otherwise 0. And we want to memorize this, and that's all. Oh yeah, we need to add some default values. Hopefully this is easy. Yep. And 210 and accept it. So yeah, I think yeah, you need to know this technique, the DGDP, to solve this. Easy work. Yeah, I think I'm not gonna lie, I first messed up the leading 0 condition. So all this was pretty standard for me, but I had to iterate a little bit to get this one as well, the leading 0 parameter. But yeah, I mean, as soon as I read it, I realized that it was this kind of problem, DGDP. And yeah, you need to demystify this technique. It's not that complicated. It's just you are going over the digits and keeping track of the information, remembering the information you need to satisfy some condition. Here you should think about this expression. If you think about it, when d is less than or equal to the least significant digit of n, then is essentially just dividing by 10, dropping the least significant digit, which means that you continue with the next digit on D. However, if D is greater than the least significant digit of N, then this is equivalent to divided by 10 and then subtracted 1. And that is updating the bound, the upper bound. So yes, this is very standard. You need to understand it. And so yes, in the end, there's a long line, but the rest is pretty, if you know what it means, is pretty straightforward. So yes, that's all I have. Let me share my solutions. So yeah, let me share this one, which is the most interesting one for Q1. Then here I have only one. Here yes, this is with the prefix sums, and the last one for the hard. Do you know this technique? Are you there, smart coder? Do you know this technique of the DGDP? It's good practice to code this solution so that you internalize it. Okay, so that's all I have. It wasn't too bad, this contest. I saw DGDP explanation by BetSimp, but your explanation went over my head. I need to rewatch. Yeah, I didn't dive too deep. There are better problems to explain the technique, because this one required keeping track of a lot of things. I mean, it has 6 parameters. I'll try to find a simpler problem to illustrate the technique. But I would suggest you to solve it on your own with whatever you can reconstruct from what I said, and then you can go over the explanation once you try it for yourself. Do they ask DGDP in interviews? I don't think so. I'll be surprised. This is more for the contests, I guess. Well, it was literally from a contest. Love your videos. Thank you. Yes, I'm gonna keep doing them. I'm glad that it helps you and it helps others, and it also helps me. So I'm gonna keep doing them. So yeah, maybe I'm gonna do another stream today, but more improvised. So yeah, that's all I have for now. Thank you, Smart Coder, and everyone for watching. See you in the next one.